right, so we're on day 2 of rates of change. So hopefully today you get that clarity or peace of mind where you understand how tangent lines, secant lines, and normal lines all truly come together. Okay, so our warm-up is to find the slope of the tangent line to the graph of f of x equals x squared minus 3x plus, or at the point 1, negative 2. So what we are going to do is kind of take what we did yesterday, and we are going to find the slope of the tangent line at that point. So remember, slope of the tangent is really the limit of the slope of the secant. So in this case, we have the limit as h approaches 0. We're going to do f of, and it doesn't matter if I do x plus h or a plus h, they mean the same. So it'd be f of x plus h minus f of x all over h, where in this case, my general form is to take the x plus h and the x and plug it in. So I picked x this time just so you could see that this is f of x, right? So that's going to go right here. The beginning part is x plus h, so we're going to plug x plus h in to get the beginning. So this becomes the limit as h approaches 0 of x plus h squared minus 3x plus h minus the original f of x, which is x squared minus 3x. And you're subtracting that whole function, which is why I bracket it, all over h. And now it's algebra. So you get x squared plus 2xh plus h squared minus 3x minus 3h minus x squared plus 3x all over h. Canceling your x squareds and your 3x. Remember, you have to write the limit every time. So it's the limit as h approaches 0 of 2xh plus h squared minus 3h all over h. I can see that I have an h in every term in the numerator, which means that I could take that out as a GCF and cancel it with the denominator. So that leaves you with the limit. I didn't understand that. Okay, Bixby. That leaves you with the limit as h approaches 0 of 2x plus h minus 3. Plug in 0 for h, and I get 2x minus 3. So that 2x minus 3 represents the general slope of the tangent. This one asks me to find the slope of the tangent line at the particular point 1, negative 2. So the slope of the tangent at 1, negative 2 would become 2 times 1 minus 3, or negative 1. So the slope of the tangent at 1, negative 2 is negative 1. And then to find the equation of the tangent line, which it doesn't ask you to do, but the equation of the tangent line would be y minus y1. So I'd be like y plus 2 equals negative 1, x minus 1, or y equals negative x, and then negative 1 times negative 1 is positive 1, minus 2 would give you negative x minus 1. Yeah, it just depends on what the directions ask. That is good. Okay, so again, we're looking at all of that again. The only thing we're adding today is called the normal line. So the normal line is a representation of the perpendicular line. Yesterday, we talked a ton about slope of the tangent. So today I'm going to give you equivalency statements. The directions might ask you for the slope of the tangent, or they might ask you for the slope of y at x equals a. So these are all ways to say the same thing. These are all ways to say the same thing. And one more, or what we're going to flow into, would be f prime of x. So that's what we're moving towards. We're moving towards 5, which is f prime of x at x equals a. These are all ways of asking for the slope of the tangent line at x equals a. Okay. So let's look at f of x equals 1 over x to find the slope of the curve at x equals a. So we have f of a plus h and f of a. So what we're going to do is look at the limit as h approaches 0 of f of x at a plus h. So that's like 1 over a plus h minus f of x at a. So that's 1 over a all over h. So again, it's f of a plus h. So in this case, a plus h is 1 over a plus h minus f of a, which is 1 over a all over h. Since it asked me to find it at the point x equals a. Now, in order to subtract two fractions, we know that they have to have common denominators. So in order to do this limit, we have to create a common denominator between the first fraction and the second. So the least common multiple would be a times a plus h. So that means this is going to become the limit as h approaches 0. Multiplying that first term, we get that it becomes a minus, because this one needs the a, the second one needs the a plus h, all over a times a plus h now, all over h. And if you recall, a fraction in a fraction says that we multiply by the reciprocal of the denominator. So we're going to multiply by 1 over h. So it cancels our denominator fraction, and that creates the limit as h approaches 0 of a, distributing my negative, minus a minus h, all over a plus h, a minus a is 0. Those are additive inverses. That leaves your top as negative h over ah times a plus h. So technically this h and that h can cancel. So that leaves you with the limit as h approaches 0 of negative 1 over a times a plus h. Now that we can plug in 0 for h, you get negative 1 over a plus 0. Well, a plus 0 is a, that's the additive identity. So you get negative 1 over a squared. So again, that negative 1 over a squared represents the slope in general for the tangent. That represents the slope in general for the tangent. The follow-up is to find the slope equaling a negative 1/4. Not the slope at negative 1/4, but where does the slope equal negative 1/4? So what that means is we want to know, when does negative 1 over a squared equal negative 1/4? Yep. So the slope will equal negative 1/4 when a is equal to positive or negative 2, which on F is the coordinate point negative 2, negative a half, or 2 and a half. So where does the slope equal negative 1/4? At negative 2, negative a half, and 2 a half. And part C, what happens to the tangent to the curve at the point A, 1 over A for different values of A. So this is kind of like question 19, part B. Can you tell me what that means? Well, let's think about what the slope of the tangent is. The slope of the tangent is -1 over A squared. The slope of this curve is then always what? The slope is always negative. There is no value of A at which that slope could be positive. So if the slope is always negative, that means as A is going to infinity, so as A is getting really, really, really big, what's happening to the function? Well, as A is getting really, really, really big, it's -1 divided by something really, really, really big. So Maddie, what happens? Yeah, it's getting really, 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 really small. That means we have a horizontal asymptote. So as A is getting really, really big, f of x is going to 0. And that would be true if A is getting really big on the positive or negative side. So if as x is getting really, really big and the function is going to 0, that tells you you have a horizontal asymptote. At y equals 0. That is the implication. What happens then as A goes to 0? What's happening to this function as it's going to 0? We know that if the denominator is equal to 0, we get a vertical asymptote. There are only 3 possibilities for a vertical asymptote. Function can only be going in one of 3 directions. As A goes to 0, the function is either going to positive infinity, negative infinity, or it does not exist. Since this function is always negative, as A goes to 0, it'll always be going to negative infinity. So that implies a vertical asymptote. So do you see the connection back to what we've been doing? Slope exploration will ultimately, hence yesterday's, which I have those for you, performance tasks involving the vertical and horizontal asymptotes. A normal line. A normal line is another way of saying perpendicular. A normal line is another way of saying perpendicular. If 2 lines are perpendicular to each other, what do we know about their slopes? If 2 lines are perpendicular to each other, go ahead, Maddie. Perfect. So the normal line is going to be perpendicular to the tangent line, which means the slope of the normal is going to be the opposite, reciprocal to the slope of the tan. The slope of the normal is going to be the opposite, reciprocal to the slope of the tan. So if my tangent slope was equal to -2/3, the slope of the normal would be equal to a positive 3/2. Opposite reciprocal. Write an equation for the tangent and the normal line for f of x at 4x or 4 minus x squared when x is 1. So we need the slope of the tangent so to the limit as h approaches 0 of f of x plus h minus f of x all over h. The algebra is the trickiest part. You have to make sure you distribute all of the negatives correctly. So it's negative x squared, negative 2xh, negative h squared, negative 4, positive x squared. Take out an h. So we see that the slope is equal to negative 2x. So now the slope of the tangent at x equals 1 is equal to negative 2 times 1, or negative 2. So the equation of the tangent line is y minus, oh, I don't know y1. How do I find y1? What does y1 represent? It represents the y value when x is 1. So it's y minus y1 equals m x minus x1. Well, in this case, my x1 is the given 1. So my y1 occurs at f of 1. So I have to plug 1 back into the original to get my y1, which in this case is 3. So the equation of the tangent line would be y minus 3 equals negative 2, x minus 1. And then it asks you to find the normal line. Well, the equation of the normal line is similar. It's y minus y1 equals x minus x1. The only thing that's changing is the slope. So if the slope of the tangent is negative 2, the slope of the normal is positive 1/2. So the normal line is y minus 3 equals 1/2 quantity x minus 1. So a nice little summary of the two. Yes, I think. Okay. And remember, all of these lessons are recorded and on YouTube. So like anytime you need to hear them or see them. All right. So the idea is this gets all the way related back to lesson 2.1, which we started with. But now we have this application of the limit. So the average speed or velocity can be represented by the slope of the secant. It can be represented using that f of a plus h minus f of a, which simplifies to over h. And then the slope of the tangent, or the slope at the instantaneous velocity, is the limit as h approaches 0, which is f of a plus h minus f of a all over h, where the a applies to the point we are looking for. The a will be the point you're looking for. So like if they say at x equals 1, that's kind of like saying your a value is 1. So let's go back and end with the example we started with. So we started chapter 2, the very first example, with y equals 16t squared. And we talked about the average speed of the rock, but we didn't talk about a general interval. We talked about an interval from like 1 second to 2 seconds. And then we talked about the interval from 1 second to like 1.1 seconds. We got infinitely closer to the instantaneous speed. Let's talk about it in general. So the average speed on the interval 1 to 1 plus h, well, this is like my f of a, and this is my f of a plus h. That's not a coordinate point, it's an interval. So that means that the average speed is 16 times 1 plus h squared, because this is your f of x, the 16t squared. So it's f of a plus h minus f of a, which is 16 times quantity 1 squared, all over a plus h minus a, which we know our ones are going to cancel to leave me with h. So I can see that the 16s cancel. I can take out an h, so they cancel. And that leaves me with that the average speed is 16 plus 16h. Sorry, that should be 2h. So it'd be 16 times 2h, which would make that a 32. Because Pascal's triangle is 1, 2, 1. Sorry, I missed the 2 on my h. Okay. So now we know that that's the average speed. So the instantaneous speed is the limit as h approaches 0 of the average speed. So if I know the average speed is 32 plus 16h, then the instantaneous speed at 1 is the limit as h approaches 0 of the average speed or that it's 32. And remember that if you're given 16t squared, that means that this is in feet per second. If it was 9.8 t squared, then it would be meters. So 32 feet per second represents the speed of the rock at 1 second. That is the instantaneous speed. Meaning that is the speed at that exact instant. It's like driving your car. Your speedometer is representative of your instantaneous speed. The speed limit on a road should represent your average speed. That's about the speed you should be driving on average. Your instantaneous speed is your speed at that precise moment. Yes. 16t squared defines the rock's position at time t. So at time t equals 1, if you plug it back in, the height of the rock is 16 feet. The speed of the rock is 32 feet per second. T equals 1 has everything to do with it. T equals 1 is the time that speed occurs. If I plugged in t equals 2, I would have to go back to part A. Yes, and plug in 2 for everything, not plug it, like that 1 is representative right here. So I'm finding the average speed of the interval from 1 to 1 plus h. But in the next part, because it started at time t equals 1, that represented the instantaneous speed at 1. If I wanted to know the instantaneous speed at 2, I would have to go back and do part A again with 2 and 2 plus h. Yes. Well, one, you don't know the derivative for complicated functions. Like you might know the derivative for this function, but if I asked you, you didn't know, let's go back to this example here. You don't know the derivative of 1 over x. Your power rule that you learned in physics does not work for 1 over x. Go ahead and try. The power rule says, okay, that's like x to the negative 1. So like eventually you're going to get into problems where like your power rule will not apply. You also don't have derivatives, which we're going to talk about next week, for like exponentials and logs. Like the power rule doesn't apply to them. Power rule won't apply to sine or cosine. So yeah, and here's the other banger, let's call it. I will not accept points for just the answer. I have to see all of the work for a limit on our test coming up. If you're in physics, cool, you can kind of know what you're looking for, but like, it doesn't work. And both parts B and D, you're doing 25 to 31 and the next worksheet in your packet. So again, it's on Fusion. It's also in your packet. You're uploading your work tomorrow morning and then working on the Chapter 2 textbook problems. You're uploading your work tomorrow morning and working on Chapter 2 textbook tomorrow.